Hi, welcome. In this video, I'll define a new operator, s squared, where this new operator has no information about direction, but so represents the magnitude of the spin vector. With that in mind, s squared can be defined as sx squared plus sy squared plus sz squared. The first natural question would be, does S2 commute with any of the spin component operators Sx, Sy, and Sz? Then we have to calculate these commutators and see if the answer is yes or no. I'll calculate the first commutator through matrix notation for a spin half system, and a second time using only the component commutation relations. The second and third commutators will be left as practicing exercise. To start off, I'll write the s squared in matrix notation, assuming what we already know. The operators Sx, Sy, and Sz in matrix notation. Therefore, the operator s squared will be these matrices squared. Finally, if we sum these three matrices, we end up with 3/4 h bar squared 1, 0, 0, 1. This is the matrix representation for the operator s squared. Now we are ready to calculate the first commutator between s squared and sx in matrix notation. By definition, it equals s squared sx minus sx s squared. We know the matrix representation for the operator s squared and for the operator sx. Then we just replace it for their matrices representation and perform the calculation as follows. Therefore, the commutator between s squared and sx equals 0. And we can say that the operator s squared and the operator sx commute or are commuting observables. Now I'll calculate the same commutator, but using only the component commutation relations. The commutator identities that will be used from now on in this example are where A hat, B hat, and C hat are operators. I won't be going into details about these identities since it would be outside the scope of this video's proposal. But if you want to be sure about these properties, a variety of algebra books bring the proof of these identities, or you can just search for them on the internet. You will certainly find. Then commutator of s squared sx can be rewritten as sx squared plus sy squared plus sz squared sx. Using the first identity, we can break down this bracket here as as sx squared can be seen as sx times sx, same for sy and sz. The second identity can be used in order to advance more in this calculation. We can think in a way to simplify this long expression with some information that we know. For example, we know that the commutator of sx with itself it's equal to 0. Now we can apply the third identity on the commutator between sy and sx. Using the third identity, it equals minus sx sy. We know the value of this commutator. The result comes from this commutator is I h bar sz. Therefore, the commutator sy sx will be minus I h bar sz. And finally, we also know the result of this commutator sz as x. It is I h bar sy. With these results in mind, we can simplify this long expression because we know now the value for this commutator. For this commutator, it is 0. We know the value for this commutator and this commutator. It is minus I h bar sz. And for the last two commutator, it equals I h bar sy. We just need to reply the commutators for their results. We ended up with the same answer we found for the matrix notation as it should be. I'll leave with these two commutators as exercise, and the answer for them are also 0, which means that s squared is compatible with all three spin components. Thanks for watching. Bye for now.